Okay, so now we're going to discuss arc length. Now, we're going to be looking for the arc lengths of curves, and one criteria is we want the arc length to be finite. So a rectifiable curve is one that has a finite arc length. A sufficient condition for a um, curve to be rectifiable is that the derivative of the function on the interval from a to b is continuous. Such a function is called continuously differentiable. So if the derivative of a function is continuous on an interval from a to b, that function is called continuously differentiable, and that's a sufficient condition for a curve to be rectifiable. And we call such a curve a smooth curve on the interval from a to b. Now here is the definition of the arc length. So let the function y equals f of x represent a smooth curve on the interval from a to b. The arc length of f between a and b is given by this formula. The arc length, which we denote s, is equal to the integral from a to b of the square root of 1 plus the derivative of the function squared dx. And that looks a lot like the distance formula, and that's because that is derived from the distance formula. So let's go ahead and find the arc length of this curve on the interval from 1 to 2, the arc length here, this distance along this curve. So what we want to do is we first need to find the derivative of the curve. So the curve is y equals, this is 1 6 x cubed plus 1 half times x to the negative 1. So I rewrite it, and then the derivative y prime is then, let's see, we have 3 6 x squared, and then this would be minus uh, 1 half 1 half x to the negative 2. So we get this function when we take the derivative, and what we're going to do is we're going to look at, we're going to plug this into our formula, and the formula is this one right here. So where the arc length s is going to be equal to the integral from a to b, which in our case is from 1 on the x-axis to 2 on the x-axis, of the square root, and this is going to be the square root of 1 plus, uh, and then we're going to take the derivative that we just found and we're going to square it. So that's going to be, well, 3 over 6 is 1 half times x squared minus 1 half times x to the negative 2. Close parenthesis, and we squared this whole thing squared, uh, and dx. We're taking the or we're integrating with respect to x. So we get this expression for the arc length, and then we just have to be able to calculate this derivative. So, I mean, sorry about that, not this derivative, but we have to be able to calculate this definite integral. So we're going to go ahead and calculate this definite integral. Okay, in order to do that, what we're going to do here is, oops, we're going to go ahead and we're going to FOIL this, giving us 1 fourth x to the fourth uh, minus 2 fourths plus 1 fourth x to the negative 4. So that's what we get when we FOIL all of that. And everything else remains the same. Well, since all the denominators are 4, I'm going to change this 1 into a 4 over 4. And this is an equivalent integral. All I've done is FOIL and prepare to combine the fractions there. So let's see, 4 fourths minus 2 fourths will give us a positive 2 fourths. So the arc length will then be the integral from 1 to 2 of the square root of and then we'll have 1/4 x to the fourth plus 2/4 uh, plus 1/4 x to the negative 4 x to the negative 4. Okay, and that leads us to this integral. Well, let's see, they all have a denominator of 4, so I can factor out that 1/4, and I'll have, actually, if I factor out the 1/4, I can take the square root of it. Let's save that. We'll do, this is going to be a factor of 1/4, and then on the inside I'll have x to the fourth plus 2 plus x to the negative 4 dx. And this on the inside can be factored actually. Um, that factors quite easily as, let's see, we still have the 1/4. And to factor that, well, to get the x to the fourth, we need x squared to be multiplied by x squared. And to get the x to the negative fourth, we need x to the negative 2 to be multiplied by x to the negative 2. And if we square this, we actually get the expression inside of the parentheses here. So that's the factorization of that. And the next thing is we can actually go ahead and take the square root of both of these things separately. So we'll have the integral from 1 to 2. The square root of 1/4 is 1/2. And the square root of this squared is just x squared plus x to the negative 2 dx. And this is a relatively simple integral to take. Let's see. This is going to be 1/2 times, um, if we integrate x squared, we get 1/3 x cubed. And if we integrate uh, x to the negative 2, we get negative x to the negative 1 power. And we are taking this from 1 to 2. So here we have an expression for our arc length. Let's see. If we plug in 2 into this, we will get 1/3 times 2 cubed, which is 8, and then minus 1 over 2, which is 1/2. Alright, so that's the first part. And then we subtract what we get when we plug in 1. So if we plug 1 into this, we'll get minus 1/3. And then because we're subtracting, this would be plus 1 over 1, which is 1. So we get this expression that we can actually get a number from for the arc length. Let's see what we have here. We have 8/3 minus 1/3 is 7/3. And then negative 1/2 and plus 1 is 1/2. So inside of this bracket, we can get a 8/3 minus 1/3, 7/3, uh, and then plus 1/2. And 7/3 plus 1/2. Well, let's see. The common denominator is 6. So this would be 14/3 plus, or sorry, 14/6 plus 36, 17/6. 17/6 times 1/2 is 17/12. So there we found the arc length for that curve. All right, let's take a look at one last example. Let's take a look at this curve, y equals the natural log of the sine of x, and we're going to do that one from pi over 4 to 3 pi over 4. So the first thing we would do here, once again, is we would find the derivative. Y prime in this case is equal to, well, the derivative of the natural log of the sine is the derivative of the sine, which is the cosine of x over the sine of x. And the cosine of x over the sine of x has another name. We also call that the cotangent of x. Cotangent of x. So the derivative of the natural log of the sine of x is the cotangent of x. And now we're going to plug that into our arc length formula. So the arc length is going to equal, is going to be the integral from pi over 4 to 3 pi over 4. And we're integrating the square root of 1 plus, and then y prime is the cotangent, so this is the cotangent squared of x dx. All right, so this is going to give us our arc length. So let's see, extend that page a little bit. All right, so this is the integral that we are going to be calculating. So 1 plus the cotangent squared by the Pythagorean identity is actually the cosecant squared. So this becomes the integral from pi over 4 to 3 pi over 4 of the square root of the cosecant squared of x dx. And the square root of the cosecant squared is just the cosecant. So this turns into just the integral from pi over 4 to 3 pi over 4 of the cosecant of x dx. That is the integral from pi over 4 to 3 pi over 4 of the cosecant of x dx, which was one of the integrals that we were supposed to learn from Calc 1. This is actually equal to the negative natural log of the absolute value of the cosecant of x plus the cotangent of x. And we're taking this integral from pi over 4 to 3 pi over 4. So we're going to plug pi over 4 and 3 pi over 4 into this integral, or into this expression. Let's see what the result is here. Okay, so this would give us negative, oops, need a pen. This would give us negative natural log of the absolute value of the cosecant of 3 pi over 4, and the cosecant of 3 pi over 4 is the square root of 2, plus the cotangent of 3 pi over 4, which is negative 1, and then that would be minus negative natural log of the absolute value of the cosecant of pi over 4, which is also square root of 2, plus the cotangent of pi over 4, which is 1. So we get this expression, and this is actually equal to the natural log of the absolute value of the square root of 2 plus 1 over the square root of 2 minus 1. And that would be the arc length of the function. I'm creating